Here we have the active attachment I used for UNISA iSet Robotics M1 and M2 MOOC assessment challenge. It attaches to the medium motor in the front of the robot, and because it's for a catapult for mission 9, for mission 8 I think, it has a lot of recoil, and the difficulty with it being detachable is that it's maybe not as sturdy as an attachment like this would be if it was a built-in part of the robot or attached directly to the motor. Maybe if you look on YouTube, you'll see quite a few EV3 videos of EV3 Lego where they use a large motor to drive catapults because of the shape of the large motor of the EV3 robot. But the motors that come with a spike prime are harder to use because they don't have round heads to drive catapults attachments around. So even though it's quite easy to attach this, I made it more secure by using these eye pins to make them semi-permanent, but not too difficult to remove. So for the coding of the catapult, I had to trial and error work out which angle, starting angle and finishing angle, would work best to get the sweets to have a trajectory that allowed them to land into the cup and not hit the cup at the front, or not fall too short, not go over the top of the cup. I attempted to use Lego elastic bands, but the results were variable. Maybe the elastic would stretch a little bit between launches and then not have the same amount of elasticity. So I stopped using them before the final version. Then the knob gears in the end were the gearing system I chose because they are unable to mash and go past each other. So the device functions the same way. It's reproducible. It's very reproducible. For the motion, I decided to go with a certain amount of degrees. So the starting position would be 0 degrees, and the finishing launch end position would be 60 degrees. So catapult would go between 0 degrees relative position and 60 degrees relative position, and then return to 0 degrees. Despite having a passive attachment to weigh the robot down, during the minute that you had to launch sweets, the robot would still continue to move slightly in a counterclockwise, anti-clockwise rotation. And so I built into the code a repeat loop that while the launching was happening, the robot would move right or clockwise and keep the yaw angle of the robot at 0 where it had started its program. And if it was going in a negative yaw direction, it would then turn clockwise or do a right turn to maintain its direction and keep the yaw between -1 and +1, so at 0. During the challenge, the other challenge was to use sensors, so I used the ultrasonic sensor to make sure that my catapult was the same distance away from the cup. So because I calculated that it needed to be about 51 centimeters away for my calculations of angle and power percentage to function. And then I also used the ultrasonic sensor during the around the block mission, so the robot would stop when it was 23 centimeters away from the edge of the game mat on the 3 sides, which have a wall, and start turning leftwards, do a left turn every time it was 23 centimeters from the wall. The color sensor was obviously used extensively, and the color sensor needed to be placed in a unique position due to one of the rules being that your wheels may not cross over the black line. So the color sensor needed for the line following needed to be placed outboard of the front wheel, and that would keep the wheel outside of the black square in the middle of the board. What I also noticed with the line following was that if I chose quite a when you were trying to use reflected light intensity, if you chose the usual reflected light intensity for a line following algorithm, the wheel would be on the line, and I wanted it to stay off the line, so I chose a reflected light intensity that was not halfway between black and white, so that the wheel would remain further away from the black line during the proportional algorithm that I used. So during the 4 units of M2 UNISA iSet M2 MOOC, I enjoyed building a few of the active attachments. So I followed the advice to look up dog gears on the internet, and so I built quite a few dog gear attachments using knob gears and changing of direction with gears inside of the mechanisms. Another interesting attachment that I saw that would be very useful was attachments that can grab and lift, so with the use of one motor. So instead of using one motor to grab and another motor to lift, this attachment will grab, and when it can't grab any further, it will lift. So through controlling the range of motion of this attachment in its various formats, you would be able to grab and lift. And here's another one using a worm gear, also a grab and lift attachment. So it was a good learning curve to learn the different benefits and disadvantages of the worm gears and other gears in that process. This rack and pinion that I used to build a forklift attachment was also a very exciting one to build. Not quite sure if it fits onto this exact model, but it works quite nicely and has a large range of motion, and would be able to be used in quite difficult missions that required you to move objects or that are at quite a high height above your robot, or at quite a wide distance to the side of your robot. Lots of fun and lots of learning.